Here we go. Let's knock this stuff out, y'all. Focus. All right. We're going to divide ionic compounds 3 ways for right now. Okay? We have binary. We have transition metal. And we have polyatomic. Now, all of them have some similarities and some obvious differences. Okay? Let's start with the similarities first. All ionic compounds have a cation and an anion. The cation is positive, the anion is negative. The cation is listed first. Now what's that for? Let me recalculate. The other thing we have to know is that all ionic compounds really just all compounds have a charge of 0. Right? What's a binary mean? 2. Two parts. This is your traditional metal plus non-metal. Okay. In the case of a transition metal, what's going to make a transition metal different? What do we know or not know about a transition metal? It's the number of valence electrons, which means we don't know its oxidation number, right? Many, so 2 or more, right? So a polyatomic ion is 2 or more non-metals that make an ion. All right. What you got? Metal plus non-metal. Oh, you don't know the number of valence electrons, thus you don't know the oxidation number. All right. We okay here? May not have it all written down yet, but I'm going to slide this over here so it's out of my way. All right, for ionics, write what you see. No prefixes. Still use I at the end if it's binary or transition metal. All right. If this is transition metal, you need to put the transition metal charge as a Roman numeral. The naming is easy. So writing it when it's binary, you gotta realize it adds up to 0. Okay, obviously there's a duck on the list. It's sometimes a little bit hard. Okay? Let's see how that works. We okay here? So those 3 make sense. All right, what you see? All right. Got flip? Yeah. All right. We're going to start from the bottom up. I have to know my oxidation numbers. On the back of my periodic table, I should have made a chart that shows the oxidation numbers. So I should have something that looks like this. Remember this one? Remember that table? It's on the back of your periodic table, or it should be. It should be on the back of your periodic table. Okay. All right. So potassium is an alkaline metal, so it's got oxidation +1. Chlorine is a halogen, it's got oxidation -1. So I've got my charges here, right? Since they add up to 0, it's neutral. I pretend that they're not there, and that's how I got KCl. Okay? Does that make sense? Because all compounds have to add up to 0. All right? They do add up to 0, but because they share electrons, they share them weirdly. Because you're looking at valence electrons and not their oxidation. All right? What you got, Mary? Right. +1 -1 adds up to 0. All right. Look at the next one. Next one I gave you was Mg and F, right? Okay, what's the charge on Mg? It's a +2. What's the oxidation on F? -1. Does that add up to 0? No. Okay, since it doesn't add up to 0, I can do one of two things, depending on how you like to think. You can either do what's called the drop-in swap, or you can do what's called the I-bar. You're going to get the same answer either way. Now, if I do what's called the I-bar, I need to look for the lowest common multiple of 2 and 1. Lowest common multiple of 2 and 1 is 2. So on this side, I got to get a total of +2 compared to -2. How many +2's do I need to get to +2? 1. So I'm just going to have 1 Mg. How many -1's do I need to get to -2? I need one more to give me 2. I hope I have a reasonable answer. 11:30. Okay, so, all right, listen. Okay, you can do, if they do not add up to 0, you can do lowest common multiple. Lowest common multiple between 2 and -1 is 2. So if I have a +2 on this side and I need +2, I just have 1, so I just break the symbol. If I have -1 to get to -2, I need 2 of them. 1 + 1 is 2. F2. The other way to do it is what's called the drop-in swap. So this 2 comes over here. The 1 comes over here. But I don't write the symbol if I use it, or I don't write a subscript if I use it once. But I get rid of my charges. So I have Mg F2.
Wait, what? Oh, I like that way better.
I don't write a subscript 1 if I use the symbol once.
Oh, so just like
I get the same answer, yeah. I just swap it.
That's so much different. I'm gonna use that.
I don't care which way you do it. You're going to get the same answer. But this shows you why you have the balance of charge. Okay? This just does it for you. Okay. You never write the pluses and the minuses. You never write a subscript of 1. Okay? On the third one, Al2O3 aluminum oxide, you swap the 3 from the aluminum down to the 2 of the oxygen, the 2 from the oxygen over to the 3 of the aluminum. Okay? Alright, let's get into some transition notes before I put Nathan and Jack to sleep. And I might have already lost time. Alright, let's try one of these. Okay. Alright. What? What's the name and what's the difference?
Looks like iron oxide.
They are both iron oxide. But what's the difference? What's the charge, right? How do I figure out the charge on the iron?
You have to.
I can undo the crisscross, right?
Oh,
But there's no numbers here. So what do I do?
Right one.
I can't write 1, but they have to be equal and opposite, right? What's the charge on O? -2. So this is an understood -2. So what does this have to be? Equal and opposite. +2. Because it has to add up to 0. So what's the name of this? Iron 2 oxide. Because it's a transition metal, I have to name its charge. Okay.
Those like two separate little like examples.
These are two separate examples.
Oh, okay, yeah, that's what.
They're both forms of iron oxide, but I'm using it as an example of why you have to name the charge in a transition metal. What's up? Because if I don't show subscripts in a binary compound, that means the cation has the same magnitude of charge, but opposite in sign. Okay? Equal but opposite.
So did you write like negative to positive because you can't write one?
I had to write -2 and +2, but because oxygen, if I look at the back of my periodic table, has an oxidation number of -2.
Oh, it sure does.
Because it's in the oxygen group. So therefore, iron had to be equal yet opposite. All right. So it's +2. Okay? So on this one, I can undo the crisscross, moving the 2 up here and the 3 over there, turning this into Fe3+ O2 minus, which gives me iron, what form?
Iron
3 oxide. Okay? You see the difference? What you got here? Oxygen is always a non-metal, right? So when this 2 comes back over to the O, it takes the oxidation, the positive or negative of whatever this is. Oxygen's a non-metal, so it's negative. When the 3 comes over to the iron, it then has to be positive.
That charge is not 0.
Right, but this, when I write it, does not add up to 0. Reason being, because if I add it up on its own, it adds up to +1. But if I do lowest common multiple of that times that, 3 times 2 is 6. That's a +6. 3 times 2 is -6. +6 -6 is 0. So when I multiply them by their subscript, it does add up to 0. But the oxidation number on its own will not add up to 0. That's why you do the drop-in swap, is when the oxidation numbers on their own do not add up to 0. Great question. What you got, Robert? I feel like I stopped over you. You got it? Okay. You do the drop-in swap because the oxidation numbers do not add up to 0. Now I feel like we won. Okay. We okay here? Do you want me to give you like a handful of like 5? I want you to try them?
Yes.
Okay. It's like the wrong time to go pee, Mr. Gallon of Water Man. Please. We compared the difference between iron 2 oxide and iron 3 oxide and why they got their name.
the big old switch.
All right. Actually, you know what? I'm going to stop here because then everybody's in the same level of boat. All right.